Hello everyone, and welcome to the sixth webinar of these Latin American webinars. Today we have Paola Arias from Universidad Santiago de Chile, and she will be talking about. Hello everyone, and welcome to the sixth webinar of these Latin American webinars. Today we have Paola Arias from Universidad Santiago de Chile, and she will be talking about Latin American women. Sorry, I have a Nico. I'm sorry, I had a Nico. I'm back. Sorry. Well, welcome. We are here, the coordinators of the webinar, and Roberto Lineros in Valencia. We have Nicolás in Sao Paulo, Joel in Peru, Federico is in Medellin, and well, Paola here in Santiago. Let me tell you a little bit about Paola to introduce her work. She did the PhD studies here in Chile, in Universidad de Santiago de Chile, and then she was a postdoc in DESI, and then postdoc in Universidad Católica de Chile. Right now, she is associated professor in USACH in Universidad de Santiago de Chile. She returned to his first university, and well, she works on hidden photons. And today, she will be talking about shining light into the hidden sector. And well, I will let you with Paola. Hello, Paola. Can you hear us? Paola, can you hear us?
Hi, can you hear me?
Yeah, we can hear you now.
Sorry. Yeah, as I was saying, can you hear me, yes?
Yeah, we can.
Yeah, thank you, and sorry for that. This is new for me. And thank you very much for the kind invitation to this webinar. And as Germán said, I will tell you about shining light into the hidden sector. This is mainly about two hypothetical particles, axions and hidden photons. So I will tell you a bit about what they are and why we think they are there, and how can we look for them in the experiments. So this is the overview of my talk. First, I will motivate the existence of weakly interacting slim particles, or the abbreviation WISPs. Then I will tell you how can they be called dark matter candidates, some detection techniques, and the parameter space that is currently available for these particles. Then I will tell you about new ideas that we are developing to search for these particles, and I will finish with an outlook. So, going beyond the standard model, probably I don't have to convince you so much that we need to go beyond the standard model, and probably there are two ways to do that. I have some picture here. One of them is to go into power, so to build big accelerators and hope that these very massive particles that we cannot see appear in these colliders. But we also have an alternative to go beyond the standard model, and that would be to go into the realm of low energy experiments, but very high precision experiments. So I will tell you about how can we search for these dragons that might be not accessible by colliders, but they can be accessible by low energy experiments, and this low energy, of course, is a way to speak, but low energy in the sense of colliders. So the first motivation I want to do is from a bottom-up approach, or just waving my hands, that why we think that should be more particles than the ones of the standard model. So from a very phenomenological point of view, one can name the so-called strong CP problem, that probably you've heard about it. So it's observed that the strong interactions are even by CP transformations. But in the Lagrangian, we have a term that actually violates CP, which is given by this expression that I wrote here, that is proportional to the field strength of the gluons. And this term that violates CP is conformed by the sum of two different terms. One of them comes from the solution of the U1A anomaly, and the other one comes from the quark sector, from the mass of the quarks. And therefore, one can constrain this theta bar, basically, that is the sum of this angle that comes from the solving the U1A anomaly, plus this contribution from quarks. One can constrain this parameter by looking into the electric dipole moment of the neutron, and realizing that so far we haven't observed an electron dipole moment of the neutron. This means that probably this parameter should be 0, this theta bar. So currently the bound is about less than 10 to the minus 9. But probably as the experiments get more reliable, we will find that these numbers should be really, really small. So the question is, why is theta bar so small if it's the sum of two unrelated stuff? So basically, why are these two things canceling exactly? This is called the strong CP problem. And one way to solve it, that probably is the most elegant way to solve it, is to introduce a new global symmetry, which is called the Peccei-Quinn symmetry, that gets spontaneously broken at some high energy scale. And as a result of this spontaneous symmetry breaking, a pseudo Nambu-Golson boson appears. That in principle is massless, but then this Peccei-Quinn symmetry gets explicitly broken by instanton effects, and so this particle, which is called the Axion, gets a mass that is suppressed by the energy scale of this Peccei-Quinn energy. Yeah. So this particle mixes with pions, and therefore can mix also with visible photons, and then we get an effective Lagrangian that that couples axions to two photons, and the coupling constant between axions and photons is given by this G gamma gamma, which is proportional is inversely proportional to the energy scale of the Peccei-Quinn symmetry. So also is really suppressed, because we think that this scale should be higher than the electroweak scale. And therefore we end up, if we want to solve the strong CP problem in this way, we ended up with a massive boson that it's extremely weakly coupled to the particles of the standard model. Yeah. Therefore, we cannot look for this particle by colliding protons and so on, but we need to look for really precise experiments. I will tell you later how can we look for this particle. So the equations of motion of between axions and photons are written down there. If you separate the photon into a polarization, sorry, I should tell you, I should stress that, as you can see, the coupling between axions and photons is given by the product E dot B, E being the electric field and B being the magnetic field. Therefore, one could think that you need two photons in order to produce an axion. So there is a process called a Primakov process, which actually can convert a photon into an axion, and this is what I will tell you in this next slide. So as you can see in this image, we have, for instance, a region where an external magnetic field exists, and we can shine some photon into this region. If you split this photon that you are sending into a polarization that it's parallel to the applied magnetic field and a polarization that is transverse to this applied magnetic field, you will get the equations of motion that I'm showing up here. So as you can see, the component of the photon that it's perpendicular to the applied magnetic field has the equation of motion of always, so a decoupled photon. But the parallel component gets mixed with the axion, and this has some physical consequences because of the mixing of the parallel component of the photon with the axion. This component will travel at different speed, basically. So then when you combine the two after passing through this magnetic region, you will find that the observed light gets an extra phase. So this translates into an ellipticity of the beam, and basically this magnetic media acts like a birefringent media to the photons. Yeah. So this would be the first way to look for these particles, mainly to shine light into this magnetic region. After the axion was proposed very long ago, like more than 30 years ago, appeared what is called the PV-last puzzle. So in 2007, there was an experiment that was looking for measuring the vacuum birefringent of QED, the prediction. And they observed a positive signal of this birefringent vacuum, but the observation was not compatible with the QED expectation. Therefore, the axion appeared as an alternative to explain this observation, but the QCD axion, the axion that was invented to solve the strong CP problem, could not explain this signal. Therefore, people started to develop some theory, and they realized that actually, for instance, from string theory, you will get plenty of axion-like particles, so particles that are quite similar to the QCD axion in the sense of the couplings, the mass, etc., but they don't solve the strong CP problem. And people also looked into hidden photons. That was an old idea of Bob Holdom, of hypothetical particles that are vector bosons that also mix with visible photons. So they both could actually explain this PV-last puzzle. A year later, so in 2008, it was found that the PV-last result was actually due to an artifact of the apparatus, and the signal was actually not physical. But so even though PV-last experiment at the end was not finding any new physics, it actually was good in the sense of the theoretical development of new ideas, and axion-like particles actually came strongly, the same with hidden photons. And so people started to actually look for these particles. This would be the bottom-up motivation. And now I will tell you about the top-down motivation. Is that if you want to look for physics beyond the standard model, perhaps you should rethink the foundations. And one alternative, for instance, would be to look for string theory. And you will find that string theory, no matter what compactification do you use to reach the low energy Lagrangian, will lead to at least one axion-like particle. So actually, if string theory is an alternative for the physics beyond the standard model, then you will be full of these axion-like particles, and also you will be full of these extra hidden U1 gauge bosons that could emerge from a hidden sector that it's coupled at high energies. And when you compactify to reach the low energy effective theory, it will appear as a mixing between hidden photons and photons. I will tell you in the next slide. So these are the hidden sector photons. They are abelian gauge bosons from a U1 sector that is weakly coupled to our visible standard model. This was an old idea of Bob Holdom in the '85, but now people has looked into string theory models in order to generate this low energy Lagrangian. And mainly, as you can see here, we have the usual Maxwell Lagrangian, and then I have a Maxwell Lagrangian-like term for this hidden photon. The third term corresponds to the mixing between the photon and the hidden photon. So x mu nu is the field strength of the hidden photon. And this chi parameter is the so-called kinetic mixing parameter that is generated at loop level via heavy messenger, and is predicted to be small, at least smaller than 1. And the fourth term in the Lagrangian is a mass term for the hidden photon. And this mass term can be generated either by a hidden Higgs mechanism or by a Stuckelberg mechanism. And if the hidden photon doesn't have a mass, then it's unobservable, because I will show you later that you can actually make a rotation of the fields, and if there is no mass for the hidden photon, then it's unobservable. So the kinetic mixing, this term that I showed you before, can be eliminated if you for instance, make this transformation of the fields to these tilde fields. And as you can see, if I make this transformation, the mixing goes to the mass part of the Lagrangian. And if you recall, this is the same that happens with neutrinos. So actually, there is here a mass matrix that is non-diagonal, and this will lead to oscillations between hidden photons and visible photons. And this mixing does not need of an external magnetic field, as axions do, because axions are spin zero bosons, so you need to have an external magnetic field in order to get the mixing with photons. Now I will tell you a bit about how can they be cold dark matter candidates. So at the energy of this spontaneous symmetry breaking of the global U1 symmetry, that in the case of QCD axions will be the Pesce-Quinn symmetry, this Nambu-Goldstone boson will emerge, and the same for the hidden photon will appear this massive vector, and you can check that in an expanding universe, in a Friedman-Robertson-Walker metric, you will find the equation of motion that I wrote here, which is quite similar to the inflaton one. And this equation is valid to axion-like particles, and to the spatial modes of the hidden photon. Here H is the Hubble parameter, and I'm assuming here that the field is homogenized after inflation, so therefore is only time dependent and is homogeneous in space. So at very high energies, when the term 3h is much bigger than the mass of the particle, as you can see from this equation, the field is frozen. So mainly the solution of this equation is a constant, so the field is frozen. But at some time, the mass of the particle will equate the parameter 3h, and in this moment, the solution of the equation is an oscillation, so the field will start to oscillate, and this can be interpreted as that the potential of the particle of the field, changes. It tilts because of the mass, and therefore the field can roll down the potential, hit his vacuum expectation value, and start to oscillate around this value. And this is where the particles are produced, and the initial amplitude of this field is then set by inflation. So if you solve this equation that I showed you before, you will find the third equation here in the screen. And as you can see, the amplitude of the field is time dependent and is labeled here by this calligraphic A. And if you compute the energy density of these particles, you will see that goes as 1/2 than the mass square times the amplitude square, plus I put some dot here because these are derivatives of A, which, as you can see, the derivative of A goes as the Hubble parameter, so it's much less than the mass. So I neglect these other terms. The same, I can compute the pressure of the particles, and is given there. So when you compute the average pressure and the average energy density, you find the equation of motion of matter, so basically dust, and therefore these particles are born with non-relativistic, so they always have the equation, the state equation omega equals 0. So they are born non-relativistic, they are never in equilibrium with the rest of the universe, and therefore they are born cold, and they will be bi-level dark matter candidates if there is a sufficient dark matter production, if they are long-lived, and if if basically if they don't decay. So if the lifetime is bigger than the age of the universe. And as I told you, this mechanism works for axion-like particles, and hidden photons to each spatial mode. This is the parameter space where axions can live. So in the vertical axis, I'm showing you the coupling constant to two photons. And the horizontal axis is the mass of the axion. Here, this plot is valid for axion and axion-like particles. So the QCD axions live in this line, this dashed line that appears here that says axion models. And the rest of the parameter space is where axion-like particles can live. So all the colored regions are exclusion from observations, mainly astrophysical, except the pinkish and red region, which is the parameter space where axions and axion-like particles can be called dark matter candidates. So as you can see, not so many experiments are currently exploring this region where they can be dark matter candidates. We have only these alloscope searches that I will tell you, I think, a bit later about it. But mainly, this is the status of the axion-like particles today. This is the same plot, but for hidden photons. So again, I'm showing you this kinetic mixing parameter that couples hidden photons to visible photons. And I'm showing you the mass of the particle. And again, all the colors regions are constraints from observations. And everything below this red line, this pinkish region, is the parameter space where they can be called dark matter. So now some detection techniques. So because of this oscillation between axions or hidden photons and visible photons, you can design an experiment called light shining through a wall. So mainly consists into shine photons and send them into this wall, that is the black rectangle that appears there. And this wall is opaque to photons, so mainly will stop all photons. But if in the way of traveling, the photon oscillated into a wisp, so either an axion or a hidden photon, this new particle can pass through the wall and therefore can be appear into the other side and be reconverted into a photon. And then you put a detector and you can then wait for a photon to appear in this detector. Yeah, this would be the most easiest way to look for these particles. This experiment has been done actually at DESY and at CERN and many other places. But the problem is that the probability of observe a photon into this detector is really small, because you need to multiply the probability that a photon will convert into, let's say, an axion in the first region, and then the probability that this axion in the second region will reconvert into a photon. So therefore, to make this experiment, you need a very powerful laser, for instance, that can shine many photons per second. And you need to have a really good detector, because you need to count single photons, basically. So this is what I meant at the beginning with that you can look for these particles by using high precision experiments. And as you can see, also, well, in the case of axions, you need a strong magnetic field to enhance the conversion. Also, you can use the sun as your source of photons. And these experiments are called helioscopes. So basically, you know the predicted flux of photons that should reach the Earth, and then well, you can constrain these particles either by the lifetime, for instance, of the sun, which actually places a huge constraint to these particles. And the other one will be to perform a light shining through a wall experiment, but using the sun as a source. of photons. This third idea is something that we are working currently with Benjamin Koch of the Universidad Católica de Chile, with Georg Jäckel from Heidelberg and Javier Redondo from Zaragoza, which consists in to look for hidden photons using this setup. I will tell you what it means. So this yellow cylinder is a solenoid that will produce a constant magnetic field, for instance, in the Z direction. And then you put a superconducting coat, superconducting shielding, into this solenoid. There will be a small vacuum in between. And if the hidden photon does not exist or does not mix with photons, if I put a magnetometer outside the superconducting shielding, I should observe zero magnetic flux. But if a photon can oscillate into a hidden photon, actually the hidden photon can escape the superconducting shielding, and therefore if I put a magnetometer outside the shielding, I could observe a magnetic flux different from zero. Of course, this magnetic flux will be really, really small, so I need a very powerful magnetometer. Currently, the most sensitive magnetometers are squids that can detect around 10 to the minus 18 Tesla. So this would be the idea. This is the graph or the plot that shows the behavior of the magnetic field without hidden photon. So from 0 to 1 is the solenoid region. Then from 1 to 5, I put this vacuum region. And then the magnetic field inside the superconductor is exponentially suppressed. And therefore, if I'm choosing, of course, the right superconducting shielding, I should not observe anything after the shielding. And this would be the same plot, but assuming that photons can mix with hidden photons. Therefore, I can have a magnetic flux outside the shielding, and this could be detected. Another idea that we were working on to detect hidden photon dark matter in this case, we did this work in collaboration with Babette Dobrich from DESY. She's an experimentalist, so she helped us a lot into develop this idea that it's based in a similar idea for axions, and it works like this. So if the hidden photon is the cold dark matter of the universe, it oscillates in time, as I show you in this equation before, and has a constant amplitude that does not depend on the space. Yeah. If I put this expression for the hidden photon into the equations of motion, assuming so this kinetic mixing with the normal photon, you will see that the Maxwell equation changes. And I have a source term for a magnetic field, so, and would be this minus chi and the derivative of the hidden photon field with respect to time. And this term therefore behaves like a displacement current. Yeah, so I would have this condensate of hidden photons that permeates the whole universe, and therefore should be a tiny Lorentz invariance violation, because as you can see, this can generate a magnetic field that will have a fixed direction in space. And I would like to then try to measure that magnetic field. And so it works like this. So because the dark matter, the hidden photon dark matter, has this amplitude oscillating in time with a frequency equal to the mass of the particle, you can see that part of the energy of the cold dark matter will be invested into the creation of a visible electric field that you can compute by taking the derivative of the field with respect to time. And therefore, this electric field that again will permeate the universe can be a source of a magnetic field because oscillates in time. And the idea is then to enhance this signal using an LC circuit, so a circuit with a capacitor and an inductor. This would be the sketch for that. So mainly you have here this loop. So with the loop, one expects to catch up the magnetic flux, the change in the magnetic flux of the dark matter. And if there is a change in flux through this loop, we know that a current will be generated in the loop, and this current can be amplified by this LC circuit. Basically, if you tune the product L times C to the mass of the particle. So then this current will get amplified, and you can put again a magnetometer in the inductor of the circuit and try to measure some very small flux, magnetic flux in the, and not a hidden photon. I think we cannot hear him.
Okay.
Now we can hear.
Okay, sorry. No, would you run the experiment with a different magnetic field, or it's not necessary?
I'm sorry, I missed you at the beginning. You said that the experiment, what, sorry?
If you need to run the experiment with a different magnetic field to see the magnetic dependence of the
okay. Okay. So to answer that, again, let me go, for instance, to this light shining through a wall. So let's assume that I detect some photons after the wall. Then I wouldn't know if this was because of an axion or because of a hidden photon. But then I could, for instance, repeat the experiment, but with the magnetic field switch off. Because of course, as you can imagine, the experiment is done always with the magnetic field on, and you can use it to axions and hidden photons at the same time, basically. You can constrain both. But if you observe something, then you should turn off the magnetic field or changing it, making it stronger and then lower, and see if the signal depends on that or not. And then you could discriminate between a photon and an axion in this kind of experiments. In the one that I show you, for instance, in the superconducting box, this is only possible for hidden photons. Yeah, because even if I produce an axion, I don't have a magnetic field to reconvert into a photon. So, for instance, this experiment would be only sensitive to hidden photons and not to axions.
Okay, thank you very much, Paula. Do we have any other question?
Yes, I have a very short question. No, just
Okay.
it's regarding to the WISP reconversion or WISP production, because in most of the cases, depending of the strength of the magnetic field. But I was wondering if it is possible to, I don't know, by via Higher operator or something like that, to be dependent to a strong gradients of magnetic fields instead of the absolute value of the magnetic field itself.
So you
I
mean,
mean,
for instance, a magnetic field that depends somehow in space or in time?
exactly. It could be a strong gradient, for instance, like a needle of magnetic field, or something like that.
Yes, this is a very interesting question, because actually, yes, it is possible to enhance the probability by tuning, for instance, either the time dependence or the spatial dependence of the magnetic field to the mass of the particle. So you could think in this oscillation between a photon and a wisp like a two-level system. If you recall, a two-level system, for instance, like the spin of electron spin, for instance, you can have this Rabi resonance. I don't know if you recall about this effect, but mainly tells you that you can tune the external input that you are putting with the frequency of the natural frequency of the two-level system. So actually, there are works where people is considering, for instance, a spatial-dependent magnetic field, and if you can tune this spatial dependence, of course, should be periodic, the spatial dependence of the magnetic field. So if you're thinking in a needle, this should be several needles equally spaced in space, and then you will find an enhancement in the probability. I don't know why. Probably it's hard to do this experimentally. I'm not sure, because currently there are no experiments exploiting this, but there are works that show that you can enhance the probability of conversion by using this space oscillating magnetic fields. And actually, we are also looking now with a colleague from here, with Jorge Gamboa, what will be the effect of having time-dependent, oscillating time-dependent electric fields, magnetic fields, sorry.
Okay, thank you.
Okay, thank you, Paola. Is there any other question? If not, we will thank you very much, Paola, again, for this very nice seminar. It was very interesting.
Yeah, thank you.
And I think people get very interested, especially in Colombia, in this project. And well, just to say that, well, we will have a new webinar in 2 weeks, and we hope to have many of you attending to this. Okay, thank you very much, and goodbye.
Thank you. Bye-bye.